Right, good morning, everyone. We're ready to get started. This is session 1, MasterClass. My name is Michelle Arnold. I will be your moderator for this session.
Do I need to get everyone in here?
So our first speaker is Terri Johnson. Terri Johnson is the Director of Public Sector Services at INRIX, where she brings over 30 years of experience in intelligent transportation systems and traffic management. An engineering graduate from the University of Wisconsin, Terri is a leader known for her expertise in leveraging big data to help state departments of transportation, metropolitan planning organizations, and cities make informed decisions. Her passion lies in harnessing data and analytics to improve safety, reduce congestion, and empower agencies to plan and optimize their roadway networks. Terri resides in Dallas, Texas, and is the proud mother of 25-year-old twins. Please hold your questions till at the very end of our 3 presentations, but please help me welcome Terri. Thank you.
Thank you. All right, can anyone hear me? I know it's a different speaker, different microphone, I mean. You can hear me? Yay! Before we get started, I want to thank 2 people who have saved me in this whole presentation here in the back, Ken and Tyler. Thank you for taking care of all this. So before, I am curious, how many of you use ChatGPT? Oh, wow. That's pretty good. I was at a conference the other day, and I was mentioning it to someone. They hadn't even heard of it. I was like, are you kidding? Where have you been? All right. Well, this abstract was actually written by someone else who's going to do this presentation. And so I put the abstract into ChatGPT and said, hey, write me a 30-minute presentation on this abstract. And it actually did a pretty good job. But I have to say, I really didn't use much of it because it needed to be trained. And we're going to talk a little bit about that. I would have had to iterate a bit more. But anyway, I'm going to get in some definitions because I didn't realize that all of you were just so advanced in this world of ChatGPT. I guess is it all the young people, or are some people my age? I'm in my 60s, so is anyone in the 60s into this ChatGPT stuff? So I'm going to go through some definitions and then a few examples of how we're using it in a project that we're doing, or we just started with Caltrans. So in short, AI is computer software that mimics the way humans think to perform complex tasks, and AI is not new. It's been around. It's been in our industry for a number of years, but also it really started in the 50s, and it doesn't this look like something that we had seen in kind of our first semester computer class? This type of little diagram, but I'm going to say machine learning is simple to simple. We've been doing this forever. Then we have deep learning, which takes complex inputs and then gives us simple outputs. And then where we are today and where we're most interested is in these foundational models, where we have complex inputs and then complex outputs. So to get into I know this is probably like I said, 101, but machine learning, it uses algorithms to train data to produce models that can perform simple tasks faster, and then high-level definition process that allows machines to learn from data without being explicitly programmed. And this allows us to identify patterns and improve themselves over time. So one example of machine learning is kind of what INRIX has been doing, and many other of you have been doing, which is basically, for us, taking pro-based data and calculating travel times, doing traffic predictions, incident detection, and so that's, this has been around for a long time. So next we have deep learning, and deep learning is sort of the next level of machine learning, where there's multiple layers of processing, and I'm going to just read this, are used to extract progressively higher level insights from data. I think I did get that little definition from ChatGPT. So in our industry, there are many different ways to use this. So we're using it by taking some of our trip path data, and then we have to normalize that data as we get different providers, so that we can use that data so it's more consistent, and make sure we're delivering this consistent type of data. Another way that we're using deep learning is in our parking product. So we have a multiple level approach of looking at both real time and historical and parking data, and then also parking patterns. And then we can predict, we're doing this in New York City, we can predict where there's space available in the New York City area. Now this is what everyone is talking about, this whole generative AI, and it's really the foundational models. Most people are familiar, obviously, with GenAI, and I guess in this room with ChatGPT, and it's currently trained on large language models. And the things that you can apply to it is gathering like text, creating images, composing music, 3D simulations, and we think we've heard a lot about this in the industry. That all encompasses AI, right? And so it's funny because people use AI in so many different ways. They're like, oh, AI this, AI that. Well, those are a few examples, but what AI is not, it's not like a black box that's going to magically give you answers. And it's not going to replace humans. It's a tool that needs to be carefully deployed based on specific use cases and specific inquiries. So one of the things that we've learned is setting the right expectations. Just because you have a lot of data and you connect data sets to data lakes, and then you go and you put it into an AI platform, it doesn't mean you're going to get answers. AI is not a traffic engineer. What we've done is we've really tried to set expectations with the people that we're working with and innovating, and we're not testing a product, we're innovating a solution, because AI is not necessarily a product. We're creating a solution. And because of some of the biggest expectations we run into is people think that what we're doing is going to be the cure. And I think people have too high of expectations about what really AI is going to do for us. And some of the challenges we've learned this year is the GenAI language models, they want to give you answers. So if you ask ChatGPT, or even any of these types of models, the models that we're working on, give me a recipe for a cake. Well, some of the models that we're training on for traffic, it'll try to give you an answer. And it's going to always give you an answer. And you always, just a heads up on ChatGPT, you need to check what it tells you, because it's not always true. So it'll always give you an answer. So then so with the machines, you have to be very thoughtful about testing and kind of building guardrails. And I'm not sure if anyone understands the amount of human testing that we've had to put in some of the examples that I'm going to tell you about. Job displacement may be overblown a bit, and I think people have whatever opinion they have, but there was all this frenzy when computers came out, right? Everyone's like, oh, computers are going to save all this time, and they're going to be commonplace, and they're going to take a lot of jobs away, and I'm not sure if that's necessarily the case. It just kind of shifted in the jobs that we have today. Now, scalability, this is how we're building the platform and how it grows over time. You have to be careful when you're building this kind of thing, because there's a lot of data and there's a lot of data costs, and you have to focus on the cost, processing time, how long is it going to take to get the answer. So scalability is really something that you have to consider when you're building this type of platform. And then overdependence. Someone at our company said this, and I thought that was interesting. They talked about how they had to take a class. I don't know, George, did you have to take a class on how to deal with consultants? Believe it or not, this was a big deal in California. I remember those days where they had to take this class, and they had to, first they were like, oh my gosh, yeah, consultants, they're going to take our jobs away, you know, kind of the fear of that. And that was part of this training. And then on the other hand, end of the spectrum, it's, oh, well, consultants, I'll just, you know, they have the scope of work, they have what to do, I'm going to leave them alone and let them do their, you know, their work. Well, we know how that, well, many of you probably, well, there's consultants here, but you know how that can go if you just let those consultants go. You gotta monitor them a little bit. Well, it's the same with this AI and this, is that you really have to be in the middle, and you have to test, you have to make sure that you're a part of this process. And then we talk about privacy. Well, obviously at INRIX, we have to take privacy very, very seriously. And again, you know, I don't know if all the companies you work with will let you use ChatGPT. I mean, my daughter works at Deloitte. They can't use it. They have to use the Deloitte, you know, internal AI. And because it's because of privacy. Well, someone on our team was at a conference and said that there was someone from an agency who said they were going to load the RFP responses into ChatGPT and ask it to give a summary of these, just so they didn't have to read all of them. I thought it was very clever. But what you have to realize is some of that stuff is confidential and proprietary. So you really be cautious of what you're putting in there. I know there's probably some permitting things and different things. I think John Hibbert was saying that are, you know, confidential at the DOT. So just be cautious of that. There's a lot of different resources. Okay, did anyone in here help write any of these? Has anyone written stuff about AI, machine learning? I need a hand. I need someone to raise their hands. Okay, okay, thank you, Todd. Because then I'm going to have you ask them if you have any questions about this. You can just go to them. So we want to make our data more useful, and so we created INRIX Compass. We're working with AWS, and the goal is to leverage the 20 years of data that we have to inform faster and more effective decisions, and then even effective approaches. And these are just some of the, you know, questions we're trying to answer. You know, our goal is to answer these questions. What do we want to be able to quickly pinpoint issues? We want deeper insights to determine like root causes of what's happening, get perspective on the recommendations to solve these issues, and then predict the impact of those solutions that we are proposing. So that's what we're hoping this will all do for us. We have a bunch of data, okay? You can see that in that slide. We have, so how this process works is we have to form that data that I just showed you on that slide is really the building blocks of the Compass solution. So agent architecture, it's like an air traffic controller. It interprets the query, you know, the query based on the text that's submitted, and then it understands where the query goes and then directs it to the right location so that it doesn't have to like go through all the different systems. So that's kind of how, I don't know if that makes sense, but in my head it does. Additionally, we allow customers to bring data. So for our project with Caltrans, they're providing the crash data, asset inventory, equity indices, and points of interest. And then we build in a knowledge base. These are different specifications, and then we go in and we start to train it using this data. Again, because of a lot of this is in the tech space, we spend a lot of time doing prompt engineering, which it takes a lot of time and testing. And so taking written prompts, and then you're setting the context, guiding the large language model in analyzing the prompts. And then it takes a lot of time to make sure that those prompts actually make sense and they're input into the right area. So we're testing and testing and testing this. And then, I don't know if you're familiar with ChatGPT in the sense that it doesn't have a good sense of space and time. So once again, we have to build algorithms into it so it can understand geographies and the geographies that we're dealing with. But last but not least, here's where the humans come into the loop, is the humans test our model responses, and we use the feedback to refine and iterate and iterate and iterate and iterate. Here's our first example. This is where we've applied GenAI to our first use case. This is understanding the causality of abnormal congestion. So we want to take what we've done is we've taken the INRIX real-time data flow map and product that we have, and which we call mission control. And then we add our data lake data sets listed here into this model. So this is San Antonio, and you can see there's a congestion alert on the top right. And what we're doing is our system, currently provides, probably using some machine learning and some deep learning. It provides a location, a description. Here it says delay 3 minutes on I-35 southbound in Randolph Hills, average speed 15 miles per hour. And then we include like an elapsed time and 9 minutes, and then also we tell you that the severity is moderate. But then the next step and what we're trying to test is we click and go into the compass. Oh, there we go. So when you, oops, I think I skipped. So when you launch Compass, you can see that it's processing the data in the top right. You can see the different types of data sets that it's using to process this. And then here you can see that we're querying historic data for a detailed description of the particulars of this congestion. So I know it's probably hard to read, but it's basically telling you like exactly here it is, this is the time, typically here's when there's congestion, there's normally congestion from 6:45 in the morning to 3:45 in the afternoon, but this is at 8 p.m., so this is not regular congestion. But at the time that we submitted this request, there were no weather events or no major events or holidays contributing factors. So this suggests that this is non-recurring congestion. But then we ask another question. And that question is to gain some additional context about it. So we asked, are there any crashes near this location? And the response is yes. And it describes the situation. It's basically telling us that there was a crash on a kind of an adjacent roadway, and that roadway is closed. So it's giving us some pretty decent information. And I mean, obviously, we're hoping that this will be something that will help in operation centers, where you can start asking questions and getting more information back really quickly. The other use case is Deloitte Consulting and INRIX we were the selected vendors to investigate near misses and injuries, fatalities, to identify risky areas and monitor interventions designed to increase safety for vulnerable road users. And this is with Caltrans. We're working on this. We just started this project. So hopefully someday I or someone else who's working on this project can come back to you and fill you in on how it's all working. But so we're currently working on a network screening and prioritizing the workflow. It typically, like this whole workflow that they were talking about can take up to 2 years to do, because they're trying to figure out where are the worst locations. Well, as we were doing our demo with them, someone from the IT department at Caltrans asked the engineers, how long would this take? And this initial phase that they were talking about would take about 8 months to a year. And the engineer said, if we have this way of collecting this data, it could really take us days, maybe days or just weeks, because it's just pulling on all this data and kind of summarizing it. The first thing that we built was a knowledge base to train. So this is be trained on existing industry-proven safety countermeasures, and these are from FHWA. And then we ingest all the previously mentioned data sets, our data sets, the Caltrans data sets, and then we asked where were the crash hotspot locations on this map. So we said, hey, where in here do we have the worst crash locations for VRUs? And then it came up, and it said, here are the 5 locations, and here are the countermeasures. And so the response, like I said, it said, here are the 5 hotspots with the highest number of crashes. It suggested different countermeasures. For the first location, it was basically, add a median barrier to prevent cross-median crashes, provide adequate clear zones, and flatten the side slopes. Well, obviously, I mean, as an engineer, you probably would have figured that out, yourself, maybe. But it's taking so much information. As you put more and more information, maybe geographies, maybe you can't do anything with the side slopes. Maybe you can't, add a median barrier. I don't know. You can add more information, and hopefully you can start really giving you a different type of answer. And then the second one, it basically said, reduce the speeds, or put variable speed limits in, and install median barriers. So this is what we're hoping. We're hoping that we can start putting all this data in. It can give you those answers so that you can really focus on doing your design. And then we can continuously ask more and more questions and dig deeper and deeper, and hopefully we can tone it down to like maybe what is the exact solution at that location. So each recommendation for these countermeasures includes an external link. And so that's another thing that could be super helpful. You can just click on that link, and it'll take you right to the page in the specification that you need to look at on the different countermeasures. And I think that would be extremely helpful to be able to do a lot of that. I know that I think Bentley and AutoCAD, some of those, they're doing a lot of this, the same type of work, trying to figure out how to make it faster and easier for you to do designs. So that's it. How to get started. You have to have clean data. You need well-structured problem statements. And then, obviously, it's nice to have an AI person. And, of course, to have an INRIX with a contract with INRIX. And I had to add that. And thank you very much.
All right, thank you, Terri. The next speaker is Ben Golke. With over 22 years of experience in the tech industry, Ben Golke is a seasoned leader and serves as the Director of Software Engineering at Rekor Systems. He has a record of building and delivering software projects of all sizes. At Rekor, he drives strategy and engineering operations in the urban mobility and public safety product families. Ben is also a dedicated educator, having taught and led instructional teams at institutions like Lambda School and the Iron Yard. Additionally, he serves on the board of Underdog Devs, a nonprofit organization dedicated to developing career pathways for formerly incarcerated individuals in the tech industry. Please help me welcome Ben Golke.
Hello, everyone. So like you said, I'm Ben Golke from Rekor, and today I'm going to be talking about augmenting vehicle classification with cloud AI-based inference. So Terri's talk was actually, I think, really helpful and informative as a foundation, because what she talked about is largely similar to what I'm going to talk about. I'm just going to sort of speak in more specific terms about a couple of things that Rekor are doing. So to start off, I want to kind of explain how vehicle classification at Rekor it works today. So let's imagine a roadway with a large truck on it, and we have that truck driving past one of our cameras. So that middle image there is a Rekor edge system. And what is contained within that package is a solar panel for power, a camera, and also a full-blown computer that can do a bunch of its own processing right at the edge. So what we do is the truck drives past the camera at a perpendicular angle to the field of view of the camera, and we then take that live video and we do image extraction to pull out those individual vehicles as they go past. And then once we have that base image, we do ML inference right at the edge. So rather than sending it up to a cloud server and having it do all that up there, we do it right on the computer at the edge. The advantages to why that might be useful compared to doing it in the cloud are it's very fast because it's happening right at the point of capture. And we also have distributed compute. So rather than necessarily investing in a bunch of cloud infrastructure, we can distribute that computing around the country in our individual units and do that base processing there and just send the results up to our server for display and for process, for reporting, things like that. So that's how we do it today. As far as what you get as an output from that, we do class count and speed, CCS, so you can see things like the timestamp of when that truck passed by that camera, the classification of the bin 13, which one was it, the direction of travel for that, because we know that from installing the camera and which way the roadways are pointed. We can also do it per lane. So rather than just giving you kind of an aggregate view of all the vehicles that pass by the camera in total, we can tell you actually which lane that vehicle passed through, if that kind of delineation is something that is important to you. And then we can also do instantaneous speed. So as the vehicle passes by, again, at the edge, we can figure out what their instantaneous speed is, record that, and then send it up to the cloud. So that's what we do now. That's today. But what if we could add more context to that and make it more interesting, give you more insights than just the basics of class, count, and speed? So to do that, to harness that additional insight, we need more horsepower, and it's really more horsepower than we can reasonably put into an edge unit. So we want to augment the work that we're already doing at the edge and bring that data up to the cloud and then use the horsepower there to expand and do more. So back to that example that we looked at a minute ago, the beginning of it is the same. The truck drives past the camera. The onboard edge unit does that basic CCS, class, count, and speed. And then it sends all of that data up to our software interface called Discover in the cloud. And you get things like a real-time dashboard. You get reporting on the different classes and things like that. We also send up the image and sometimes some of the video as well. And what that allows us to do is then bring it down to that lower right corner, which is we pass that data off to an AWS instance where we have a lot more horsepower and we can do a lot more deep classification and processing. So for example, what you might want to do is pull, let's say, the class 9 vehicles from the data set that you pull from the edge and bring up to the cloud, where you know it's class 9, but you don't really have a lot more insight besides that. That's all we get from CCS. What if you wanted to then drill down and say, I want to identify logging trucks, like the truck that's listed there, right? We can see that as humans, we can tell it's a logging truck, but the system that we have designed is not currently trained to be able to understand that that's specifically a logging truck. It just knows that it's a class 9. So let's say we then take those class 9 vehicles, we pull them all up to the cloud, we do this additional processing, and then we can figure out which vehicles specifically are a logging truck versus just sort of any given class 9 vehicle. So that's an example of one of the kinds of things that we can do using the edge data and then adding in that additional processing in the cloud to get more specific insights. Terri did a great job of explaining basically this slide, so I'll be quick about it, but essentially with expert level models, a lot of training is required. So let's imagine you wanted to understand the make and model of a given vehicle as it drives by. You'd have to, with traditional sort of supervised learning methods, you'd have to grab a ton of images of Mazdas and Fords and Toyotas, and you have to train the model on how to recognize a given make and model of a vehicle. So it's a lot of input work, it's a lot of data collection and then processing. But what you get out of it at the end of it is you get a highly trained expert level model that's really good at identifying makes and models. The thing that it's not so good at is anything else, right? The whole point of that is to create a very narrowly focused algorithm that can give you make and model, but it can't do much else. So we do that today, right? That's a lot of what happens at the edge. But we want to take these different modalities of input. So it talks about images, video, text, and other kinds of data. We could train individual expert models on all of that, but then that's a ton of work and a bunch of training. What if we could fuse them together and then use more of a foundational model, like an LLM, like ChatGPT, to give us more general insights into what it sees and what it identifies? The advantage to that is you get a broader selection of results. You can ask it questions and you can usually get answers. Sometimes they're not the answers that you want, but they are always an answer. So we want to combine really the power of both, right? That highly trained expert model that's really good at one thing with then the more general foundational models that can give us additional insights into whatever it is that we're looking for. So if we were to take those two examples from before, it's really the same example, that logging truck. In the way we have it today, we can identify class count and speed, we can get location because of where the camera's located, and we can get things like the date and time, stuff like that. What if we combine that result set with the deep classification we could do in the cloud? Suddenly you have a lot more availability of information to you. So you can see all those things I listed are in this result set, but you also have things like type of vehicle, load characteristics, if it's a semi-truck, like is it carrying lumber, is it a tanker, is it a dump truck, is it a box truck? We can get that kind of specificity. We can get color, we can get body type, is it a sedan, is it an SUV? And we can then do, at that point, with all that extra context, near real-time or historical analysis on all that stuff across different locations, depending on where the cameras are listed or posted, to give us all kinds of different interesting conclusions from all that. So let's take a look at a couple of examples. So we've got deep classification, example 1. What this is showing, as you can see here, is a tanker truck. We can tell that by looking at it, but the computer can't necessarily do that. So we have the original PVR record, which contains the stuff we talked about, right? Timestamp, classification, direction of travel, things like that. That would all be captured at the edge and provide you with that basic information, and you can get that today. If we combine that with these new data points, we can get things like what orientation is the vehicle traveling in respect to the camera angle. So this, in this case, the 3 o'clock position, right? Headed 90 degrees from north. We can see, does it have any logos? We can check the actual image, the truck itself, and say, are there any identifiable company logos or other kinds of logos that might be useful to determine what kind of vehicle this is? How many wheels does it have, right? What's the axle count? You'll notice in this example, this is an example of it being not quite right. So you'll see the truck has 5 axles, as is pretty standard, but it's saying that it has 6 wheels, and that's because it's actually capturing all 5 of the axles of the truck and that front axle of the vehicle behind it. It doesn't understand at this point that those are 2 different vehicles, right? That's something we'd have to further train on and refine to make sure that it could differentiate. But today, that's what it does, right? It's mostly correct, but it's actually more correct than it should be. It's grabbing the car behind it. Other things that, again, you can't get easily with the way that we do it today. What kind of cab is it, right? Is it, in this case, a day cab truck or a sleeper, which this to me, it looks like a sleeper truck, so not quite right? But it's got a little confidence. What kind of trailer is it? What is it carrying, right? With a standard bin 13, you don't necessarily get a lot of that specificity. So in this case, it says flatbed trailer. I'm not a semi-truck expert. I'm not sure if this would be considered that. Probably not, because it's specifically a tanker, but either way. What's the function, right? We can take a guess at what this might be used for. So you get those basic raw data points that are in addition to what you get from the edge. And if we bring that into our cloud software interface, then we can build reports and other things to give all of you insights into different things about what you might want to drill down on. Rather than just, let's say, a class 9 or a class 3 or whatever, you can say, give me a much more specific question, and I might be able to give you a much more specific answer. And then in the vein of ChatGPT, we've been working with LLMs as well to provide more kind of summarization, right? Oftentimes the raw data points aren't as interesting or necessarily even informative to look at by a human. It'd be better if we could get like a description, a summary, right? A lot of the INRIX examples showed plain text summaries of just a paragraph of information that any engineer or really anyone could read and hopefully glean useful insights without having to comb through raw data. So this is another example of that. You can see it says the image shows a large tanker truck likely used for transporting liquids or gases. It seemed to have gotten that right. It's got a silver color. It's parked on the street. This is a still image. It doesn't understand that the vehicle's in motion, so it thinks that it's parked. The truck is operated by a company. It must have gotten that off of the side of it or something, and it specializes in transporting hazardous materials. So we can do things like look for those hazardous material placards to see, what's what about that. So really, we can take that raw data and we can then turn it into a summary that might be useful to really anyone who might want to look at it. Let's look at number 2. So similar idea, we get that original data from the edge on the left side, and on the right side, you can see that it's correctly identified the 5 axles, 5 wheels of that truck. It says that it's logging cargo, so it can actually tell that it is not just an empty flatbed, but that it actually has cargo on it. And then it says that it's a semi-truck, it's a function. So in the description, it talks about it having a flatbed trailer with wooden crates on it. So it's actually correctly identified through the image that not only is it a truck, a trailer, but it also has specifically wooden crates as its particular cargo. So it talks about maybe using it to haul construction materials or lumber, right? Again, it's taking a guess, but over time, we can refine those insights to make them more accurate and more useful. Let's look at number 3. So number 3 is a little bit different. It's not a semi-truck, it's a box truck. And in this case, I think a little more interesting because we're not just sort of looking at the truck generally, maybe it's cargo, but in this case, this is a Penske truck, so we're able to identify the logo. You can see it's telling us that it's pointing left, right, in the 9 o'clock position relative to the camera. It counted the logo, counted the Penske logo, 2 wheels, 2 axles, and then identified individual strings of text on the truck. So you can see it's a little bit hard to read because the image is very small, but it identified Penske at least. It's the largest text on the truck. And then depending on the resolution and size of the image, it could be more or less accurate identifying the rest of it. So in the description, it talks about it being a box truck, got that right. Yellow and blue striped design, got that correct too. Stuff that you wouldn't expect a computer system to necessarily give you, that specificity on by just looking at an image. But that's the power of these foundational models. It allows you to get insights that wouldn't be easily possible before. It tells you that the back of it is covered in advertisements. It's technically correct because it's advertising Penske. And then it's operated by the Penske company. It even identified not just the word, but actually that it is a particular trucking company. And it just says that it kind of gives you a generic answer at the end that it's likely used for transporting goods and cargo. So what does this give us? What does all this extra data give us in the end? It gives us the ability to be flexible and to provide a lot more interesting insights and specific data to our end user inside of Discover. And then for us, it also allows us to do things like, what if we determine that our system doesn't perfectly classify, let's say, class 4s or something like that, right? A particular bin 13 class is not well represented by our training data, and therefore at the edge is not doing a super great job identifying that particular class. What this new power allows us to do is, rather than just necessarily going through and doing a whole ton more training to try and make that better, and that's going to create incremental improvements on that accuracy. If we can bring it up to the cloud, we can say, okay, rather than pulling in all of the data from every camera on every class, that would be an inordinate amount of data that would be difficult to process in a timely fashion. We can say, well, we're going to use the power of the edge-based processing that we've done to only look at that particular class, pull up those particular images and PVRs, and then do that additional processing in the cloud with our declassification to improve the process of classification of that particular class. And whatever we learn there with that big horsepower in the cloud, we can then work on miniaturizing and bringing back down to the edge to then kind of, in a positive feedback loop, make the edge processing better. So in addition to giving extra power to our customers, it also allows Rekor to constantly improve our processes and make our products better and more accurate so that then they're more useful for customers. It's, again, a virtuous cycle. That's it. Thank you.
Thank you, Ben. Our last speaker is Dr. Angshuman Guin. Dr. Guin is a principal research engineer in the School of Civil and Environmental Engineering at the Georgia Institute of Technology. His research is focused on finding an answer to the question, how do we enable and empower system managers, researchers, and users to make effective data-driven decisions? Dr. Guin's current research projects at Georgia Tech are broadly in the area of traffic operations, connected and autonomous vehicles, and machine learning. Please help me welcome Dr. Guin.
Thank you. All right, let me ask you this. Do you ever get the feeling that you are talking to machines? Yeah, the answer could be, yeah, all the time. Or, now you need to unplug, man. Oh, that sounded more like the metrics in my head than when I said it out loud. But yeah, means that's the that's where we are. Means whether we like it or not, means AI is here. Means you feel like the emails that you are getting are written in ChatGPT, the papers that you're reading, the abstract starts with the words, "Sure, I can write a 250-word summary of your document." As people are copying out the prompt in the, anyway. So that's where we are. Means, but how how do we use machine learning effectively in transportation? We heard a couple of great examples from Terri and from Rekor. But so what are we doing? Means we are essentially more or less taking the classic problems that we had and approaching them with an ML twist. What I'm going to talk to you here about today is how are we using machine learning to do more effective emergency vehicle preemption. So in this specific project, so we are trying to do preemption for hero vehicles when that's North Avenue. If you know Atlanta, so that's North Avenue. That's the downtown connector. The emergency vehicles are taking that exit from the southbound direction, going around on the loop, and trying to get back onto the northbound direction. So that interchange, like any other interchanges in Atlanta, is heavily congested. It slows down the vehicles, and it takes a long time to do that maneuver. Also, there is the Emory Hospital there on Linden Avenue. I can't point from here, but on the Linden Avenue, there is the entrance to the emergency entrance to the hospital, and the ambulances that take that exit, they also tend to get stuck in the traffic. So we are approaching this problem with to use ML or use connected vehicles, essentially, to solve the problem of reduction of delays for the emergency vehicles. And we are leveraging ML for doing that optimization. We have like 19 intersections in that study site that we are optimizing for this problem. So when we talk about emergency vehicle preemption, the first image that comes to my mind is probably that the emergency vehicle blinking some code at the traffic signal, and the traffic signal turns green for the emergency vehicle. That's the traditional check-in, check-out kind of a model that we have had probably for the last 50 years, off and on. In some places we have used it more than others, but so the next step there is not only giving the emergency vehicle a green signal, of course, after serving the pedestrian phases and such. It's not only giving them the green signal when they are close to the intersection, but try to provide them the minimum delay by clearing the vehicles at the intersection ahead of their arrival. So we have been able to achieve some of that by using GPSs and some central processing when the signals are connected to a central server, we can know about the location of the emergency vehicle ahead of time, and we can plan for it. So start the green earlier. But the trick here is not to minimize the time of preemption that we are providing. Why? Because once we could always open up all the signals on the path of the emergency vehicle as soon as we know that vehicle is going to pass through that signal. Means we can hold it green and let all the vehicles clear out so that the emergency vehicle doesn't have to take any delays. But the problem is, of course, the cross streets. Means they will be stuck there forever, and you will leave a mess in your way. So we came up with this dynamic preemption logic. This is still not ML. This is a deterministic solution where if we know the queue length of the vehicles that are stopped at the stop bar and the number of vehicles in between the front of the emergency vehicle and the stop bar, and so we can come up with a solution based on the headways of how long it will take for the emergency vehicle, or it will take for the vehicles to clear out, and you start the preemption accordingly. But the critical piece here is that knowledge about the queue length and the number of vehicles there. It's unless you know that accurately, means you cannot compute that deterministic solution well. So this is where ML helps us. So we assume that we do not, all we have is the blips or the count of vehicles from these upstream detectors that are probably 140, couple hundred feet upstream of the stop bar. So we get the approach of the vehicles, count of the vehicles. We use that, use the signal state, the distance of the emergency response vehicle from the signal head, and put them into the black box, train a neural net model, and get the preempt status, 0 or 1. That is whether we need a preemption right now or we don't right now. So the thing here is we do not have a lot of this information to train on, right? Means we are currently not running a lot of preemption, so we don't have that data. What's the best solution there? We can't pick it from the historical data. So we are generating the historical data with simulation. So we simulate it on a corridor. We run a preemption vehicle through it, collect the data, train the model. But for every one instance, say, let's say we have one emergency vehicle, one preemption in 15 minutes of simulation time. So for that one point where you have a preemption, you have 899 other seconds of data where there was no preemption. So you get a data set that classically class imbalanced data set problem. Right? You have so few instances of preemption of data points with preemption that it becomes a challenge to train the algorithm to do it right for the preemption, because it's seeing so many of the non-preemption points. It will train more to act like there is no need for a preemption. So we address this problem by doing somewhat of a soft labeling, where we ramp up the probability of the preemption over time. Instead of just taking those green blips there, we go with a ramped up probability at the bottom. So now to feed this, this is a supervised learning approach. So we need, usually for these problems, we need a lot of data. So the way we are doing this is we start with the lowest possible. That's, you turn the signal green as soon as you know about the emergency vehicle, and you do the high end is where you just let the system operate with no AVP, so it turns green whenever it would have done it normally. And then you do a binary search. You keep go in between those two, and keep halving it to find a time when you are not giving up too much of the travel time, or you try to hit the back end of that flat portion of the curve, so that means you are not giving up any of the advantages of delay reduction, but you are trying to still squeeze the time of the emergency vehicle preemption time, or the time in which the signal is in preemption, to a minimum. So we built a little bit of flexibility there to be able to slide further up on that curve by adding, like, accepting, say, like 2 seconds of travel time beyond the minimum. Yeah, so these are some results here. So the orange one here on the right hand side. So the left hand plot is for the emergency vehicle preemption duration, The right-hand plot is for the emergency vehicle speed. So on the left-hand side, a lower number is better. On the right-hand side plot, a higher number is better. On the right-hand side, the orange one is the case with no preemption, where you're getting speeds of about 30, 31 miles per hour. And with the light green one, that's the basic check-in, check-out preemption. The magenta one is the deterministic solution, and the yellow one is the one we achieved with the machine learning, which is slightly below the optimal, that's the dark green one, but it still beats everything else, all the classical models there. Now, when we approach the problem of emergency vehicle preemption, means when we are doing these simulations, we typically end up assuming that all the vehicles are behaving normally. But they don't, right? When there is an emergency vehicle behind you, you are required to pull over. So how do we take care of that? And so VISM by default does not have a checkbox that you say enable pullover behavior. So there are a lot of things, information or variables that go into the modeling of the pullover, right? Means when do the vehicles actually start pulling over? Can the emergency vehicle, what happens how do you model the emergency vehicle going over the center line, or making a right turn from the left of the other vehicles, or what's the following distance between two emergency vehicles when they're moving in tandem? When do the vehicles start moving back into the active lane, right? Well, how do you model a case where there is a partial pullover, means you don't have enough space, you are opening up half the lane for the emergency vehicle to go through. So we used a feature called the external driver model, EDM, in VISM to kind of take all these variables and come up with an emergency vehicle behavior model and a model for the response of the general vehicles to the emergency vehicles. Essentially, you're looking at the influence zone around a vehicle. You're looking at what the vehicles, some vehicles in downstream of you, some vehicles upstream of you, the vehicles on the next lane. And basically, our model comes down to, for the general vehicles, it comes down to this, where you have, if there is an emergency vehicle about 150 feet behind you, you move over. And if the emergency vehicle has passed and is about 330 feet, about 100 meters ahead of you, you move back into the lane. And I don't know if this will play or not. Yeah, it does. So that's an example of what we got with, in the VISM simulation. You see that vehicle move over and move back into the lane. And the emergency vehicle will try to attempt to move over to the leftmost lane so that they can, that's where the fastest lane is, or they can get on the left shoulder. So these are some results where we are comparing the pullover behavior, like what if we integrate the pullover behavior and then compare it with the emergency vehicle preemption. So on the leftmost chart, you have the orange block is for the no preemption scenario, and the yellow and the green, those are for the preemptions with normal exit and in-step exit for coordination. On the next one from the box from the left, you see that when we introduce pullover behavior, that orange box dropped significantly, and even below the yellow and green on the leftmost box, right? So this one is even below these two. So the question arises, like, do we really even need preemption? Means with the pullover behavior, it seems like we are getting better results than preemption. But if you have preemption along with the pullover behavior, you're getting even better results. So there is an effect. Now on the left-hand side, On the left-hand side, we had we assumed idealized behavior. Like as soon as the emergency vehicle comes behind you, you move over. But that's not how it actually works. Means people get confused. Means they're like when an emergency vehicle comes behind you, like what do I do? Do I go forward? Do I go through the signal? Do I pull over? Do I go over to the shoulder or just slow down or pull over to the left? So people take some time to react. So we built in that reaction time into the model, and so we call that the realistic model. And again, we worked with ad hoc numbers. We need to fine tune those numbers, but we see that in this comparison, means oops, sorry, the orange box still came down, but not below the preemption cases. So there is some room for improvement even without the pullover. But here, this picture, and I know it's a little busy, but this one shows the actual benefit or for doing the emergency vehicle preemption with the pullover case. Is on the left-hand plot, you have the time from the start of the entry of the emergency vehicle, and you have multiple cycles. This was on a 160-second cycle that we are testing. So you have you see that about the fourth cycle, so you have the minimum travel time of the non-emergency vehicles on the path of the emergency vehicle. So the vehicles that are reaping the benefit of getting the green along the main line. So those vehicles have the minimum travel time 4 cycles into the preemption or after it has ended. Whereas on the right hand side, that's with the pullover case, you see that it's you get that a little earlier in the 3rd cycle there. But the orange line on the right-hand plot, that's the case where you have pullover and no preemption. And the yellow is where you have preemption and pullover. What you can see there is the emergency vehicle preemption is essentially creating much less disruption. So if you compare the orange on the left plot to the orange on the right-hand plot, means you see kind of a disruptive behavior based on the rest of the traffic from the emergency vehicle preemption, which is somewhat mitigated by the AVP for the main line. So even if you are not gaining too much on the delays for the emergency vehicle preemption, you are doing a lot to save the rest of the traffic from a disruption, is what we are observing. So that was the work we have done so far on using supervised learning. Now, that requires a lot of data generation. And see, we have run like couple thousands of simulation runs to generate the data to train the model. What we are now using is reinforcement learning, where the agents, so every traffic signal is an agent, and this agent interacts with the simulation in real time or in real simulation time. So it's interactively running the two, so we don't have to sit through the night, run simulations or run batches of simulation. We start this program and let it interact with the simulations to learn from it. So much more simpler in terms of the training. So that's where we are. It's where we have implemented or built successfully some supervised learning models, deterministic models. That's where we started. We built the neural net models that worked fairly well. Means we built in some more realistic behavior to integrate with it, and now we are trying to achieve better results with reinforcement learning, trying to smooth out this training process so that it's not as onerous as it was in the previous cycles. Yep.
Thank you, Dr. Guin. Now it's time for questions. If you have any questions, please ask your questions in the mics that are going around. This is to help with our live streaming to the virtual audience. So with that said, I'll open up for questions.
Or nope, still morning. Hey everybody, Catherine Johnson, certified data nerd. I have a question for Terri Johnson about INRIX. I really like how you're integrating all the different data sources, and I wanted to ask if we're limited to adding additional data sources, for example, weather data. In Metro Atlanta, anytime a driver sees rain droplets, they hit their brakes, leading to a 60% increase of crashes. So adding this into our machine learning would really help us understand a little bit more about why we have those types of patterns. Are we able to add in additional data sources like that?
Is this on? Oh, it is. Good thing I didn't talk. I mean, yeah, that is something that we're doing and we'll continue to do but we're not there necessarily yet. But yes, we can add in all different types of data sources. And you're right. I mean, it's not just in Atlanta where they do that. It happens. I mean, I've lived in a lot of different cities. It happens everywhere. So, yes.
That's refreshing to know. Thank you, Terri. My next question is for Ben.
Yes.
And, okay, with your detectors that you have, how many locations would be ideal to get the insights that you're looking for?
So in the deployments we've got so far, I believe we have, don't quote me here, but I think it's somewhere around like 40 or 50 in South Carolina. And I think at that point, having that number, we've definitely seen a good amount of insights. You might be able to get away with a little bit less than that, but that's the number that we've seen so far.
Sounds great. Thank you. And then for Dr. Guin, just not a question, but I would love to see the pullover theory for interstates as well for Hero. We have over 600 Hero assists on that 10-mile stretch of the downtown connector every month. 600 every month. So would love to see how that could go. I know it's not a question, but I appreciate your work. Thank you, guys.
And I'll be happy to take any feedback or pick your brain on how to model that better.
This question is mostly for Ben, but I think anyone can answer it. How do you see, say, traditional practices within, say, GDOT business practices as a barrier to implementing some of your technology? What comes to my mind is so much of our counts are collected through tubes right now, and we have so many practices built around that. You know, the way we do line items has tube counts as part of it. So how has that acted as a barrier, and do you see a future where we change those practices and have a little more cost-effective solution?
Sure. So the solution that we provide with the camera and the solar panel and all that stuff is obviously very different from the tubes that you're talking about. And it is it's a different pricing structure, but it's also a different value prop. So sort of, I think our challenge so far has been in that vein, basically convincing DOTs and other customers that the tubes that you're using are getting you, I think, the basics of what you need, but the solution that we have gives you so much more. So really it's about if the value prop that we're providing is something that we can convince customers that they can really gain that value, then I think the transition has been pretty straightforward. But where maybe that isn't quite as obvious, really what for us is it's kind of like faster horses versus a car, right? Like we're trying to really present a different solution that isn't just an incremental improvement over the technology that's been around for 50 years. It's really kind of a different look at how to solve those problems. And so that's been, I think, our challenge is just sort of really educating customers on what is possible with the system that we provide and what you can get and what you can get over like those tubes, for example. In South Carolina, I know that we've been working with them on contraflow during hurricane season, which we're still in. I live in Florida, so I'm also somebody who's paying attention to that kind of stuff. So for example, we've provided ways for that customer to not only get the class count and speed, but because we have those cameras deployed across the state, they can get a live view of certain key roadways. And in the case of contraflow, which is where they basically run the traffic in the other direction during a hurricane for evacuation, they want to understand when is the right time to do that. And the thing that's cool about our solution is because of the wealth of data that we collect, we can actually get that insight through the processing that I talked about. And rather than, let's say, giving you like a raw report of just traffic numbers that then you as an engineer have to look at and sift through and understand, okay, when is the right time to turn this lane around and make it go the other way, we can actually use the sort of the power of machine learning and AI to just give you that recommendation. So we can say, now is the time, based on everything we've seen with all the data collection that we've done, now is the time to make that determination. It's just something that isn't necessarily as easily doable with something like tubes. Sure.
Second question, Terri, this one mainly directed at you, I think. Sometimes I feel AI can be a bit of a black box, and I wonder, are there certain scenarios where you have to balance using a simpler model that takes into less data into account, such as regression or maybe just an if statement over a more complex AI model? And how would you balance that interpretability with the complexity and kind of maybe a more accurate solution?
Can you ask someone else that question?
And any AI.
You know, I knew you would ask something that would be really challenging, because you always do. How do I answer that? Oh yeah, I mean you can train things with just smaller amounts of data and asking basic questions, right? Or you can ask more complicated questions, but then you have to do more testing and training and data. So I guess I don't know if that really answers it. But it is a black box, and I've learned so much. I mean, it's really interesting because it's going to give you answers no matter what. And I mean, those of you who have been using ChatGPT probably know what I'm talking about. It might give you an answer that doesn't even make sense. And if you keep drilling down, so I think you just have to identify your use case of what you're trying to solve, then make sure that the data that you put in there is the data that is related to that question or the use case that you want, and then understanding what you want to get out of it, and then put the knowledge, you know, the specifications or the documentation in, and then that's what you kind of would focus on. And I just think it can get you the data faster. And it's not like you have to look at the answer as an engineer, just like any software you use. You know, any software you use, you know, you have these young engineers that come in and they put the data into, you know, a software platform, and they give you an answer, and you go, did you actually look at that answer? Because does it even make sense? So I think we have to treat this whole AI black box stuff, you know, this AI, the same way we treat different software packages that, you know, that we've had. Like, so does that make sense? I don't know. I ramble a lot, so I don't know if that makes sense. Take with it what you want. Let's get a professor. Yeah. Excuse. Why did I just not give him the microphone? What was I thinking?
I just wanted to give him a simpler answer.
Oh.
It's like, so if you're trying to build a decision support system or build in decision support into your system, means sometimes it's a good idea to start with something simple, something that you can really trust, and then upgrade into a more complicated one.
That was what I was trying to say. Yeah.
But that comes with means you have to take that with a grain of salt, because there is always that risk that the simpler system that you are implementing might not give you the results that you want, and you might be tempted to give up early on that. So that's the rub.
As a teacher, I often used to tell my students that when you're doing deterministic programming, the computer doesn't tell you what you want. It doesn't give you what you want. It gives you what you tell it to give you, right? So new programmers often have this problem where they say, I have a problem that I'm trying to solve. Here's the algorithm that I wrote to get the answer, because they believe the algorithm will give them the answer that they want. But that's not actually what's happening. What's happening is it's giving you the answer that you programmed it to give you. And so if your interpretation of the solution versus the computer's are different, you're gonna come to loggerheads. You're not gonna be able to reconcile that. And with deterministic programming, that's the crux of it. Is bugs are basically the addition of context and nuance that the human believes they're putting in, but maybe they're not putting it in correctly or whatever, and they get the wrong result. And with AI, I think the problem for somebody who's been a career software engineer is that the computer doesn't really work that way anymore. Like in a sense, it is able to, in some cases, understand a little bit of nuance and context in a way that a computer sort of traditionally programmers haven't found to be true. So with the addition of AI into our tool set, I think like all that's been said here, you have to be very careful about what you're asking and what kind of context you're providing on sort of how those results will look. And maybe sometimes the overhead of that training and all that stuff isn't worth it. And so in that case, maybe a deterministic solution is better because it's simpler, but like the doctor just said, right, may or may not actually give you what you want. And so you have to sort of balance how general versus how specific do you want to be when you're asking your questions and getting your results.
And I thought like, what you said and what you guys are saying is there's so much training that goes on.
Yeah.
I didn't realize how, I mean, I think on one of my slides, like thousands of hours of training just to get to where we are today. I mean, just you get an answer and then you go like some of the examples you had, you got an answer and you're like, well, it wasn't quite right. So I need to put in some more information so that when it processes it, it's going to give me the right answer. Oh, it doesn't give you the right answer. Oh, I got to add more information. I don't know if I mentioned it, but on one of our products, we have, did the answer, was it a good, did it answer your question, yes or no? Was it a partial answer, or was it, not a good answer, or good, so we're asking those questions as we sit and try to train the model to figure out what else we need to put in, what other knowledge we need to put in order to get the right answer. It's way more complicated than I could ever imagine. And I mean, you look at Google, and I have I'm rambling because we have a little bit of time, but my daughter's boyfriend works for Google, and he's dealing with how they now have that response, and they have so many people working on just reviewing the responses as it relates to the presidential election. They have like all these people just asking questions to see what the responses are to make sure it has the right answer. It's mind-boggling how much testing has to be done for it.
Any more questions?
Thanks. So I have a question for you, Dr. Guin, about how close are we to being able to leverage some of the models for then feeding back into the signal timing and so forth and realizing some of the benefits that you have modeled?
They work right now. The challenge is that right now the way we are going about approaching this problem means we are still unable to skip the simulation. So if we want to implement this on a corridor or in a grid in an area, we first have to simulate that and let that train the model, and then we implement it. So means in my dream would be to go straight from you take the data and you have a model that you can implement. But right now we still have that simulation in the middle, which takes a decent amount of effort to build and calibrate to the field data. So that's the drawback right now. But the models work. Means, we have those results. Means, of course, means those are not field results because we don't have an emergency vehicle going down on the road and doing different kinds of things to give us the test. So that's where the simulation comes in. But in the simulated world, the ML models have been doing great. Means they are beating the deterministic model hands down, or at least a certain percentage. But there we are. Means the simulation still needs step still needs to be there.
Thanks.
I actually have a follow-up question, if that's cool. So with the simulations, do you think there's going to be a critical mass where you've done enough simulations that you feel like you could confidently say that most traffic scenarios in the real world would have been covered by previous simulations, such that the data set's big enough that now you can go directly from model to implementation?
Yeah, eventually. So since I'm talking about my dreams, my other dream is to have this Lego block type of
Sure.
thing where you take means you have enough simulations where you have trained your agents to work with an intersection with two left lanes and three through lanes, or one left lane and two lanes. So you have different signal configurations already trained in different areas under different circumstances. So you have these agents that you can just pick and join them together to create your model instead of trying to simulate the network as is and then retraining your agents.
Cool.
Thank you. Great presentation, all. It's a question for the gentleman from Rekor. You talked about being able to do a lot of object recognition and even name recognition on the vehicles.
Mm-hmm.
Can you talk a little bit about the element of privacy and private industry concern with roadside units identifying that that's a Penske truck driving down the road or otherwise, and kind of how you guys are thinking about dealing with that?
Sure.
With your
Yeah.
investment?
I mean, identification of all this stuff is, in one hand, it's all in the public domain, right? Generally speaking, there's no right to privacy on a public roadway, but there certainly are concerns around identifying and then storing that information, right? Maybe we identify it in the moment and throw it away. That wouldn't be as much of a big deal, but if we store it for long-term use, that certainly has implications. And right now, so what you saw in that part of it is not shipping today, so we're not doing that yet. But in the future, I think when we hopefully do implement that and put it in the field, we're going to want to be very careful about sort of the way that we store. It's one thing to just sort of classify it as a bin 13, right? It's a sedan, it's a truck, whatever. But to get much more specific around the company and pretty soon, especially if you were to do things like combine that with another tool that we have, which is LPR, license plate recognition, you could start to really correlate a specific vehicle, specific company, where it goes on the roadway, if it's going in the right direction or not. We do have customers who want to be able to do things like track trucks in particular to ensure that they are going on the roadways they're supposed to go on and not the ones they're not, like weigh in motion, stuff like that. So in those scenarios, we're getting specific requests from DOTs and other agencies to do some, what I would call like identifiable kind of tracking, right? But in most cases, we want it to be as de-identified as possible, right? That's much better for us, just as far as storing the data. So I think probably what we're going to do is we're going to focus the identifiable parts of it around very specific targeted missions that we're being asked to do by the DOTs, and then in other cases, we're going to try and keep it as generic as possible because it protects everyone. I mean, that, as a software engineer, the best data that I could ever store is data that I don't store, because then I don't have to worry about the implications of privacy and it getting stolen and all those kinds of things, right? So it's going to be a delicate balance, but I think we're going to try very much to stay on the side of as anonymous as possible with only specific stuff when we need it. And ideally, even if we're tracking a truck from a port to some other place to make sure they're not driving on the wrong road, as soon as that sort of cycle is complete, we'd want to get rid of that data so that we're not storing it permanently, right? Hope that helps.
Interesting. Any other questions? Okay, hearing none. Thank you, presenters, for the fantastic job that you did, and thank you guys for attending our session.
At lunch at noon. I think we're a little bit ahead of schedule, but there should be boxed lunches out there from 12 to 1, and then we will meet back here for session 2.